My, that cow sure looks sad. Why? Well, maybe it's because she doesn't understand limits, a fundamental concept in calculus. There are three basic approaches to finding limits: the numerical approach, the analytical approach, and the graphical approach. Think NAG. N. A. G. Tonight we will be covering the graphical and the numerical approach, and tomorrow, we will look at the analytical approach. Maybe if Betsy over here watches, then she won't be so sad.
Okay, so tonight we're going to study limits, and remember what we said in class. What is a limit? It's going to be a kind of boundary that we're approaching, and with functions it's going to be as x approaches a concrete value, becomes arbitrarily close, is there a y value that we're also getting closer and closer to. So the first function that we're going to look at is this guy right here, x cubed minus 1 over x minus 1 with x not equal to 1. And you can think about your bonus question for tomorrow will be, how can it be that this is a cubic here and we get this kind of image that looks like a parabola? So how can it be that we have a cubic yet we get something that looks like a parabola? Now the graphical approach to finding the limit, and our problem is, what is the limit of f of x as x approaches 1? Well, the graphical approach is very simple. You'll see that what we do is we approach from the left and from the right. We approach x equals 1, and we see does y get closer and closer to a certain value as we do that. And with this graph, as we look at it, we see, yes, indeed, it does. It doesn't actually ever reach there because there's an open circle, but it does get closer and closer. From both sides it approaches the same boundary, which is 3. So the limit of f of x as x approaches 1 is 3. Now the numerical approach is also pretty simple. You create this table of values, and what you do with your x values is you let them get closer and closer to the value that you're interested in from the left and from the right. And we see, is there a trend? Does f of x also get closer and closer to a certain y value? And again, we see that from this side, from the left and from the right, we appear to be getting closer and closer to 3. So let's take a look at a sort of informal definition of limit that we'll be using here. So the limit is, if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. And it's written like this. That sounded complicated, but if you look at your example here. Hello, Krista. So anyway, so we have limit of f of x equals 3. So as x gets closer and closer to 1, we see that y got closer and closer to 3. Here it's the same thing. As x gets closer and closer to a certain value c, does it in fact also get closer to a certain value L? Let's start with the graphical approach here. Here's the picture of our curve, and let's ask ourselves the same question. So does this curve, as x approaches 0 from both sides, get closer and closer to a certain y value? Well, we look at the picture and we see from the left and from the right we're approaching the same y value here. So we do appear to have a limit using the graphical approach, and it seems to be getting closer and closer to 2. And then we confirm our results using the numerical approach as well. You can see right here that as x approaches 0 from both sides, we do appear to be getting closer and closer to 2. And a third quick example is this interesting piecewise function where f of x is equal to 1 if x is not equal to 2, and f of x is equal to 0 if x does equal to 2. So you end up getting this horizontal line with an open circle and a point there. And again, visually take a look, same thing from both sides. Even though the function is defined down here as 0, the boundary that we're approaching from both sides is that open circle. That's the limit, and so our limit will in fact be 1, even though the function is defined down here. And then the table of values will be boring for this one, so we're going to skip that. So as a quick summary, you have the numerical approach, and what I'll expect you to be able to do for that is to construct a table of values. With the graphical approach, I expect you to either draw it by hand or use your graphing calculator and tell me what the limit is. And then tomorrow we're going to look at the analytical approach using algebra or calculus. Alright, and before we finish up, let's look at some ways that the limit can fail to exist, because that can happen too. So take a look at the first function. We want to know what is the limit as x approaches 0 of the absolute value of x over x. Well, if we graph this thing, we see that we get basically like two straight lines with open circles on the end. And when we're on the right side of the origin, we always get values that are equal to 1. And when we're on the left side of the origin, we always get values that are equal to -1. Interrupted by the phone. It's Mr. Goodwin. So clearly, if we go from the left side here, we're approaching -1. If we're going from the right side, we're approaching +1. And these two are not the same value. So this function does not have a limit because we're approaching different values from the left and from the right. Another thing that might happen is we might get what's called unbounded behavior, where you have something like a function like 1 over x squared, where you have this vertical asymptote. And the function does increase, and it's actually from both sides approaching infinity. Remember, a limit is a boundary, or one way to think of it is as a boundary, and infinity is unbounded by definition. So here again, we don't have a limit if you're approaching a vertical asymptote like this. And lastly, you might get something like this called oscillating behavior, where you have this cool function. You have sine of 1 over x, and we're interested in, is there a limit as x approaches 0? Well, if you look at the image for this function, then you get, first you have these smooth curves, but then if you put it into your calculator, you get this kind of crazy thing happening at the origin here, and you get this densely packed zone of oscillations up and down between -1. And one of your bonus questions for tomorrow will be to explain to me what is it about this function that leads to these more and more densely packed oscillations. And your clue is just to think, okay, well, it makes sense why it goes between 1 and -1, because if you think of just a regular sine function, the number in the front, the amplitude, will tell you the upper and lower boundary, the range of the function. And then think about what this 1 over x does to a regular sine function that might lead it to have a more and more densely packed oscillation in the center here. So why does the limit not exist for this one? Well, if you look at the table of values, and even if you understand how the function works, you notice that as you get closer and closer to 0, you're moving between 1 and -1, 1, -1, 1, -1. So the limit doesn't exist because you're oscillating between two different values as you get closer and closer to 0. And then at the end here, we have this nice summary that summarizes the three basic cases of when we might not have a limit. First, remember, we're approaching from both sides, but we're approaching two different values. So there you wouldn't have a limit. And then next, you might get that unbounded behavior where you're moving upward, and you are approaching positive infinity, but infinity is by its definition unbounded, so you won't have a boundary. And then the last thing that could happen where you don't have a limit is you can oscillate between two fixed values of x as you approach c back and forth like this. So what will I expect you to do on tomorrow's video quiz? Well, there's two things. First, I expect you to be able to use your graphing calculator to make a table of values. And if I give you a certain x value, a certain value c, I want you to be able to use that table of values to tell me if there's a limit at that point or not. And then second, I want you to be able to do the same thing using a graph. So I expect you to use your graphing calculators to graph an equation and then tell me, based on that equation and based on a concrete x value that I give you, is there a limit at that x value? That's it.